All right, other. All right, so we were playing with a calculator yesterday. And we had set up a state machine with 4 states. A state where we're entering the first number, right? And we stay here as long as we type digits. And when we type a plus sign, we go to a new state where we say we just saw a plus sign. And then when you enter a digit, we go to another state where you're entering your second number, and digits leave you in that state. When you hit an equal sign, we go to a new state where we're basically waiting for the first digit to appear. Okay, so in state 1 over here, which is also like the last state, if you type anything other than a digit, nothing happens. When you type a digit, you want to clear the display and just show that digit, okay, which takes you over here. When you type a digit, you want to append it to the right of the display unless the display is a 0, in which case you just replace that 0. When you type a plus sign, we don't change the display, but we want to record the number that's currently displayed, save that somewhere so we can add it eventually. And then when you get a digit, we want to just show that digit, okay, because that's the beginning of our second number, including if it's a 0. And then as digits enter, we append them to the right, and then when you hit equal, we read what's currently on the display, we add the number that we saved here, calculate the sum, put that on the display, and then go to this state where we're waiting to get a digit, which will cause the display to clear, and so on. So that was our state setup. And how far did we get in code? I think we were entering numbers, but I don't think we were doing addition.
We're halfway through writing something.
Yeah, and if you type zeros, it ignores it, and if you type a 7, right, that starts your digit. So it looks like we had state 2 under control, right, this entering digits and waiting for a plus sign. And that's the bulk of the work, what we've already done. So refresher, we had a method called click that we were calling every time that a button gets pressed. We were just calling click and passing it the argument. So if state equals 1, we're waiting for a digit. If we get a digit, we display it and we go to state 2. State 2, if we get a plus sign, we parsed our displayed value, saved it as num1, set our state to 3. If we didn't get a digit, we ignored. Otherwise, we either displayed that digit or we appended it to the right. So state 2 is already done. So what happens in state 3? State 3, we just saw a plus sign, and we're just waiting for a digit. We're going to display that, and then we're going to go to state 4. So state 2. All right, so state 3. If it's not a digit, we're just going to return. Otherwise, we got a digit. And what are we calling our text T? I think that's all we need for state 3.
You gotta make sure you're.
Yeah, I need double equals. If it's not a digit, we return. Otherwise, we display the digit that was pressed. We set the state to 4, and we're ready to roll with that.
Oh, we need to save. What's currently on the display at this step 1.
I think we saved it in the beginning of state 2. Alright, so
Yeah.
state 1, we're entering state 2, we're typing in a number. When you get a plus sign, we go to state 3. Well, we save our number. So in state 2, if you get a plus sign, we save our display. Go to state 3. And then state 3, we get our first digit and we go to state 4. And then state 4 says we're going to do that append thing. So here we're getting our second number. Alright, so state 4 getting the second number. So if t equals, and it's the equal sign that brings us out of this, then set number 2 equal to whatever's on our display. Add those together. And then let's display that result. And then set our state back to 1. So I think that's all we needed for an equal sign. Show the sum, go back to state 1. Otherwise, if we're in state 4, we're entering our second number, we didn't get a digit, we just return, we're not going to do anything. Otherwise, we want to display that digit, and again, if the current display is just a 0, we replace it with a digit, otherwise we append it, and we return, and that's the end of state 4. And that should be the whole function. So this should be something like an adding calculator. So let's try this. 2 plus 3 equals 5. And 41 plus 23 equals 64. And it doesn't do anything goofy. It's strictly got to be digits. Oh, that was weird.
Add 5 to that. Or don't. Just hit 5 and then equal. Or equals 5.
So let's try. Yeah, I got it in a weird state. Okay, 1 plus 2 equals. So it looks like if you hit an equal sign instead of a plus, it does something weird. Or maybe not. No, that works right. All right, so basic, right, example. Nothing particularly magic going on here. And not a lot of code, right? We really had to write one method. It's just this click method. It's 50, 60 lines of code. It's not all that much, and it's just a basic state machine implementation. And we could have taken some of this behavior and bundled it, right? This kind of stuff that we're doing here is repeated multiple times. All right, so we can add numbers. So question, how hard would it be to make this calculator able to subtract, multiply, and divide?
Isn't it basically the same?
Basically. What would you really need to do?
Add support for decimal
For
floating
For
point
divide.
No, I don't want to do floating point. Yeah, you'd need that if you wanted to do a real divide. But I wasn't going to go that grandiose
You
yet.
just have to add some more states to account for the other operators.
Okay. So here's our state machine for doing addition. What if we want to do multiplication?
Add a state in between 2 and 3 that, or a state after 2 but not
But
3.
you'd have to also alter 4, right? Because
So if we do a star, we go to a different state, and then we want to enter a second number, and then when we get an equal, we want to multiply instead of add.
So we do what was when we were doing the ODP basically.
Yeah, so we can be stateful without necessarily introducing more states. So suppose we do this. Either a plus or a star will move us to state 3. And we just remember what the operator was. Make a note of whether that was a plus or a star that moved us here. And then down here we show the sum or product based on the saved operator. And that's your ODP, right? Up here we're doing something that's going to eventually affect what result we get down here. We're just saving that information, and we can save it in a state variable without necessarily having a whole nother collection of states. So let's do this really quickly. So there's some function buttons. And what do we call it? So it's click of arg0. All right, so up here we were saying if t equals plus, we're going to save our number and change state. So we really want to do is if t equals plus or minus or times or divide, right? So we can make that fancy, but we don't have to. Say what?
You can just say not digit.
Except for the equals sign.
Oh, yeah.
We could do an index of again like we did in the digit generation, but we don't have to be too obtuse here. So if we have an operator, we'll parse num1, save that. We'll change to state 3, but let's also remember what the operator was. So we'll just set operator equals t.character at 0, and we'll make operator a character. So we'll pick the first character and only character up from t and save that. And then the only other difference is down here. When we calculate this result, instead of adding, we might subtract, multiply, or divide based on the operator. So we set the result accordingly.
No, it doesn't like your character.
Doesn't like my characters. We'll find out why. Probably because it may not have a value. Insert semicolon.
Oh. Here.
Switch.
Case.
Oh.
Oh, yeah, because, okay.
There we go.
No, it doesn't like result.
Yeah, so result may not have been given a value. Which I know it will, but compiler doesn't know that, and it's not going to let me compile my code unless I do that. See what?
What if some hacker comes in and tries?
Yeah, I know, right? All right, so relatively small change, right? We added 3 more buttons. We took the character and we saved the value of the operator. We switched our state on 4 characters instead of 1. And here we do a choice of operations based on that saved character, and everything else is the same. So now I can come in here and I can say 2 times 3 equals 6, and 8 divided by 3, and that'll give me my integer value 2, and 45 times 123 equals whatever. Pretty cool. Right, so the point is that we're writing a little bit of code, right? But we're adding arguably a lot of functionality to this thing. It's always possible to write C in Java. Okay, when I first learned Java, I was writing C. When I first learned Pascal, I was writing Fortran, right? It's easy to take a language you know, and as you're learning a new language, actually be writing that old language using the new syntax, okay? But that's going to really sort of steal your opportunity to embrace what Java or any object-oriented language can do for you, right? This idea of being able to bundle things into these classes and have an object that has all this functionality associated with it, right? That's why we can pop one button onto the frame and click through and put in a line of code, and suddenly we have a multiply button, right? So as you're working on PA2 and future PAs, right, ODPs, et cetera, be thinking about that, right? Am I putting things into these little packages, these things called classes, right? And really kind of taking advantage of what that does for me. And you'll find in the case of Java, it's going to make your code a lot smaller. It's ultimately going to make it easier to work with, right? Because once you're actually thinking in those terms, it's going to feel completely natural to do this. And writing something procedural like you would in C is going to start feeling more and more awkward, right? So transitioning over to that, that's a good thing. All right, well, let's do one more thing on here.
Make it a derivative.
Add a derivative button.
Make it a TI-89.
That would be cool.
Graph
Yeah.
Just have a 42 button.
There you go. Instead of the equals sign. So let's add a clear button. So that as we're typing in a number, if we want to correct a mistaken entry, we can just hit the C button and it'll basically backspace. So same thing. We're just going to call our click method. And so what are we going to do if we hit a C? Now we could go back to our state machine, and in each of these states we could figure out what a C does, but we don't have to sort of be a slave to the idea of a state machine, right? We're still coders. We can still sort of create the universe as we see fit. And what do we really want to do when you hit the C button? We want to knock off the last entry from the display, right? If you typed in 456 and you hit C, we should get rid of that rightmost digit, that's 6, and just change it into a 45. And that's just a string operation. And it's really kind of agnostic to what state we might be in. So up here, we've got the current display text, and we've got the button that was just pressed, which is a T. So let's just put in a little bit of code right here to handle that case. So if the text we just hit was a C, let's just remove the last entry. Well, strings come with all sorts of methods. And there's a method called Substring. And you pass the two integer arguments, a starting location and an ending location. And it will give you a piece of your original string S1, starting with character start and ending with character end -1. The -1 makes things handy. So if you have a string like hello, and you say hello.substring 0, 3, this will return characters 0, 1, and 2. It'll give you HEL. So if we plug in the length of the string, 0, 5, that'll give us characters from 0 up to 5 - 1 is 4. That'll give us our entire string. So if we want to take off the last character, what should we use for this ending position? Say again?
Just the last
-1.
and -1.
Yeah, length -1. And that'll, because we're indexing from 0, so it's off by 1, right? So this will basically take us up to, and including the character before the last character. So if you hit a C button, what should we do? Display.setText, and we'll set t.substring 0, t.length -1. And we'll just return right there. Look good? So now I can hit 1, 2, 3, 5, and I can hit a C. Oh, that's, oh. Not a typo, but I used a wrong variable in here.
Yeah, don't you, because that's not a function, don't you just do t.length?
This is the length of t, which is the last character I typed. That's not what we meant to do.
Yeah.
Right, we want the length of the string that you're trying to truncate, -1. So that's actually what we called current. Alright, so 1, 2, 3, 5, and we can delete the 5. Oh, keeps getting better. Alright, we're truncating the current string. Trial and error programming.
That seems perfectly reasonable to me, from 0 to 1. Why doesn't it just return a 1 then?
Because the length was
Oh, because
bigger
it's
than
still
the size of
comparing
the
to t,
string.
wasn't it?
Yeah.
I thought that the goal for
That makes sense now.
the C clear was actually to get rid of all of them.
No, it's just a single correct.
Okay.
It's more give backspace.
But if you do all
Yeah,
of
it's a
them, it does not
backspace.
replace it with a 0.
But
So you
if you
gotta do
do
that.
all of them, it goes blank, and if you do it again, then you get, and look how many errors we can get from like one thing. Right? So it's an index out of bounds, and it'll tell us if we scroll that our index was actually -1. Right? But that causes all these other, right? It's a whole hierarchy of things at the point where this occurs. Okay, so what's the problem here?
You're not checking to make sure you've got text.
Yeah, so if the length is 0, then length -1 will be -1, and that'll give us an error. So there's a simple way to do that. So if we've only got a single digit, let's just display a 0. And what are we assuming with that line of code we just wrote? There's an assumption we've got implicit right here. We're assuming that the length is never 0. There's always at least one character.
But isn't that true with how we've set it up?
But that should be true based on how we set it up. So it's a personality test. Do you say bigger than or equal to 1, or do you say equal to 1? If you believe that your display is always going to have at least one character, you can say equal to 1. If you don't like taking chances, you could say greater than or equal to 1. But then you're kind of admitting to yourself that maybe you did something wrong, and at some point the length will be 0. But regardless, the intent is that this never becomes negative, right? Length -1. So if the length is 1, we'll do this instead. So let's run that. So 65, clear it off, and now repeated C's don't do anything.
If you start off the thing with a bunch of zeros, that still like works, right?
So if you type a 0
That's neat.
and you bang on it, it's just, and it's not ignoring it, it's actually replacing that 0 with a new 0, right? But we don't notice. So 8 minus 20, there you go.
Oh.
So what happens then? Does it, with that negative, does it include that with the 1? Does that?
So that's the answer, so I don't
Right,
think
what
I
if you
can.
clear it?
Oh, but you can't do the.
Okay.
All right, so we should only be clearing when we're in states, whatever those states are, I think. States 2 and 4.
Okay.
All right, so we should be checking that. Otherwise, we can like play with our answer.
What happens if we try to go up on an integer? Will it overflow?
It'll overflow,
Okay.
but nobody's asked the other burning question.
What's that?
What if we divide by 0?
Oh.
Eh. Okay, so not surprising, right? So divide by 0 error. Easy to catch, right? You throw a try-catch around your operation, or in your division, you could explicitly check to see if the denominator was 0. So could you make a fraction calculator with this?
Oh.
Answer is yes.
Absolutely. You could just wrap this around your fraction class from PA1. You already have a toString, right? So anytime that you take your fraction and you put it in set text, it's going to convert it to a string using your toString, and you'll see fractions up there. And yeah, it should work pretty automatically. And again, this is intentional, right? This is one of the benefits of having things be object-oriented, right? We haven't intimately tied in the nature of the things we're working with this front end, with the middle layer that's processing keystrokes, right? So, and if we wanted to add in decimal numbers, right, we could add a decimal point. And when you hit a decimal point, display that and keep going. And the only trick is you make sure you're not hitting more than one decimal point. So you can't say 2.3.4. And when you do your parseInt, instead of doing an integer dot parseInt, you could say double dot parse double. And I think everything else would just flow through. All right, so you got your key entry, you got your operations, you display the results. You'd want to do some formatting so you don't get like 80 digits, but it's going to be basically the same. Yeah.
So, crazy question.
Mhm.
So how, on a TI-89, it gives you, you're able to put in alpha, you can put in letters.
Okay.
And if you do that, it's able to use those as variables.
Okay.
So how would you make that work? in this sort of system.
So then you're starting to get into some more parsing, and we're not doing a whole lot of parsing here, right? We're parsing a number that's on the display, that's it. But you could go ahead and display those, but then when we go into the state where we say num1 equals, right, we need to start doing some expression processing and look for letters, right, or non-digits. But you know, we've got regular expression capability in Java.
Yeah, our computer's
So-
really bad at algebra.
You what?
Our computer's really bad at algebra.
I don't think so.
I mean, comparatively.
Well,
So it can do it. So yes.
Humans are more prone to error than computers.
That's true.
yeah, it kind of depends what kind of algebra you mean.
I mean, like, solve for x kind of thing.
So yeah, so that's a whole nother discussion, right? So we can write something like 5x equals 10, right? And you ask a computer to solve that symbolically. How would you do that? Well, we could be nice and throw an operator in, or we could, you know, pre-process it and put in missing things like multiplication. But yeah, it's tricky to write something, relatively tricky, to write something that would understand that and say, you know, 5 times x squared equals 50. But it's definitely doable, right? So this is what Mathematica does, or Maple, or any of these symbolic processors. But yeah, I'd say it's harder to write a program to do that than to write a program to add numbers or multiply numbers, right? Definitely. And it feels like this is pretty straightforward for people to do, although that's only after a few years of prep and then some schooling.
Well, then couldn't you make like one of those generational programs where it has a bunch of them trying to do the same thing, and then as the generations go on, it gets better and better at it?
You could, like,
You
eliminate
could do
the
that.
program. I mean, it could
I don't know
work.
how to do that.
It's
That'd
an
be
idea.
a cool project to do,
Maybe.
definitely.
I feel like something like that, it's gonna be prone to have, it's always going to have like a very, very small chance to screw up.
Yeah, like
Yeah.
people, right?
Yeah.
So when
Yeah.
you're coming up with smart systems and they're never making mistakes, I'm very suspicious, right? Because I think mistakes are not only for people inevitable, but I think for us at least they're a part of how we learn, right? Because you can't just learn from the positive examples, you gotta learn from the counter examples. But I mean, I think that's a really cool project idea.
Yeah.
Make a genetic system that learns how to parse arithmetic expressions, for example.
I've seen examples of that, like not quite with this sort of thing. I've seen computers learn how to play games on their
Yeah,
own,
yeah.
like Mario World and
Mhm.
Snake.
Yeah.
It's pretty impressive what they're able to come up with.
Yeah, and they're learning how to play it without being told what the rules are.
Mhm.
They're just
They
looking
figure it
at
out
the
themselves.
score and yeah, which is pretty cool. All right, so other questions, comments, discussion? This is all good stuff. So I posted a question on the discussions. Has anybody gotten Window Builder to work from a Mac in here? Is anybody here using Mac? Okay. All right. There's someone in the other section who's having all kinds of problems, and we've done some Googling, and it seems to be problematic.
Don't you have a Mac on your other laptop?
Me?
Yeah, I thought your other laptop was a Mac. I must
No.
have just- it could've just-
No, I've never owned a Mac, which is kind of sad. All right, so where do we go from here? So tomorrow we'll talk about PA3, right, which is coming up Friday. So we'll talk about PA3, and PA3 is probably going to be a tic-tac-toe game. So it's going to be event-driven, the same thing we've been doing with the calculator. but it's also going to require us to do some graphics. So we can display buttons and frames and text and things like that using the swing set of classes, but we also want to be able to actually draw things sort of pixel by pixel, right? And so that's what I mean when I say graphics, as opposed to, you know, here's a button, here's a checkbox, which is also graphical. So how do graphics work? How do we draw a rectangle so that you can see it on a display? So how many people here have interacted with an old cathode ray tube television set?
I think so.
Watched one or turned one on or anything like that? Okay.
It's
So
never been very long.
these are actually a good model for thinking about pixels and how we draw things. And the model still works for LCDs, although the mechanics and physics are totally different. But old CRT television, right? So big vacuum tube, okay, covered with a phosphorus material on the front, glass, right? Coated with a material that's normally effectively invisible, but if you hit it with an energized electron, it glows. Okay, it gives off light. And when you take away that beam of electrons hitting it, the glow will fade fairly quickly. Okay, but it might be, you know, visible for a short time afterward. And you can generate electron emission. You can cause electrons to come off of something by heating it up. If you take a piece of metal and you run current through it and you get it hot enough that it starts to glow red, it'll emit electrons. Okay? And these electrons can be steered with a magnetic field. So here's the setup. You have this really hot piece of metal that's spitting off electrons, and it's going through a grid so that the electrons are all coming out in a line. And now you have a pair of magnets above and below the beam, and by adjusting the magnetic field, you can cause this beam to bend up or down. And then you have another pair of magnets on the sides, and by adjusting that magnetic field, you can cause this beam that's already been bent up or down to bend left or right. So this beam is coming towards the display of the screen, and you set your magnets so that the beam is pointing right here in the upper left corner. And if you want to display a dot there, you turn on your electron emitter. And your beam comes over and it goes up and it turns and it comes and it hits right here and you see a little dot. And now you adjust the left-right magnet to move the beam over a little bit, and now it lights up the next pixel. And if you don't want this third pixel to be lit up, you turn off the electron generator as you steer the beam over, and now the beam would be hitting here, but there's no electrons, so it's dark and it's dark, and you get over here and you turn it on again, and you turn it off and you turn it on. And when you get all the way to the end, you turn off your beam, you sweep back to the left, and you change the north-south magnets to bring the beam down one line, and you start the same process again. And you do this all the way along, you basically paint your display. And when you get all the way down here, you turn off the beam, and you swing both magnets so that the beam comes all the way back up here, and you repeat. And you do that 30 to 60 times a second. You got an image. Okay, so that's how old school TVs work. But the idea is the same today with LCDs and so on. We visualize this thing sweeping across, slowly coming down, and at each point we either turn on or off the display, and it causes a pixel to light up or to go dark. When you have color, you can think of three beams, red, green, and blue, lighting three different colored pixels, and your eye and brain mix them together and get different colors out of the mix. So these little dots, we're going to call these pixels. And in Java, we can create something like the inside of our JFrame, a panel, and we can address an individual pixel with XY coordinates and say, turn this pixel on to this color, or turn this pixel on to that color. And we can draw things by basically lighting individual pixels. Okay, so there's a low-level package called the Abstract Windowing Toolkit, and there's a class called Graphics. And by playing with the methods in the graphics class, we can draw shapes, and there's methods built for us. So if we want to draw a line from one point to another, we can just say draw a line from here to here, and it'll figure out which pixels to light up. Or we can draw rectangles or ovals or things like that. So we want to know how to do that before we can play tic-tac-toe, because we want to do things like put X's and O's and draw lines and stuff like that. And we have to get into some more event-driven ideas in order to do this in Java. So we'll talk about this tomorrow, and it's mainly going to be a method called paint, or paint component. All right, so we'll start there tomorrow.